Okay, the ones that talk about uninhibited growth, so they're just, uninhibited growth just means it's getting bigger and bigger and bigger without it's not going to stop. Like in real life, normally we think about logistics, but uninhibited is just, we're just assuming it's going to keep growing, even though we know at some point it's got to level off. So 8 talks about uninhibited growth, but this one says continuous. So usually if we think about uninhibited growth, we just think of it as an exponential, a times b raised to the x, or a times b raised to the t. Okay, so you can use that one. This one though, number 8, specifically talks about continuous. So I would accept either of those formulas, but because of the word continuous, if you want to use the PERT one, p is the initial amount, E is the number E raised to the rate times time power, and time is in years. So if you look at this one, it says the deer population in a certain area was 500, so that's your initial amount. If there were 180 deers after a year and a half, so my time is 1.5 years, I have 850 deer. And it says assuming uninhibited continuous growth, so that's why I used E. But again, if you want to use the A, B to the T one, that would be fine as well. What was the rate of increase? So I divided by 500, got this. Again, this is an exponential, put it in log form, log base E, so natural log of 850 over 500 equals 1.5R. And then I divided both sides by 1.5. I got this for an R value, so as a percent, that's 35.38%. Okay, so because of the knowing that it's uninhibited growth, that we're going to just think of it as an exponential. Because they use the word continuous, I use the initial amount E raised to the RT. Okay, unlike the next one, it says it's just uninhibited decay. Okay, so uninhibited growth and decay kind of mean the same thing. It's just a matter of what your base is going to be. So that's where I use just your basic, y equals a b to the x. That's just the exponential. So my initial amount was 25. It said when the time is 10, so when I put in time is 10, there is 15 kilograms of salt. So I put my amount of 15 when the time is 10, initial amount was 25. So to solve that, I just divide by 25. I have b to the 10th equals that value. So to get this to be b to the first, remember, I raise it to the 1/10th power. So that gives me b to the first. Over here, I do this on my calculator, and I got 0.9502. Now, that just gives me what the base is. That doesn't really solve the problem. The problem says how long does it take? So I got to know the time when there's 1 kilogram left. So I put in 1 kilogram, still have 25. I found my B value. Again, the more decimal places you go on that, the more accurate this answer will be. So to solve this, I divide it by 25. I took the common log of both sides. So I said the log of this is equal to the log of this. So I use the power property. And then I just have to divide by that log to get my t value. I got 63.01, so I just rounded that to 63. My time was in hours. So then I know that that is in hours. Okay, so if it just says uninhibited growth or decay, just use your basic exponential equation. All right, so just kind of go through the ones on the back, see if you agree with those. Or this one, I guess there's one left. This one said it obeys the continuous. Oh, this one said continuous, I guess, and I didn't use continuous. So if you use the E, that would be fine as well. I didn't. I just used the exponential in this one. So there were 623 originally, so that's my original amount, my start value. And in 2005, so that's 4 years later. So when T is 4, because it's 4 years away from that, that it was 819. So I divided. I had b to the 4th is equal to this value, so I had to take the 4th root of that, or you can raise it to the 1/4 power. I got my b value. So then if I have my start value, my b value, it wants to know what it will be in 2050, which would be 49 years away from 2001. So my t-value is 49. Plug that in my calculator. I got about 17,772 cases. Now, again, you should get something close to that if you would have used the e. So if you would have said 623 e to the RT power, and said that, okay, when t is 4, so you put in a 4 here, 4 times r, and put this as 819. You would have got a different r value, but then when you plug it back, that r value back in, plug it back into that equation, you would get something very close to 17,772. Again, because of rounding, we might get a little bit different answers, but it would also work. So, you know, if you see the uninhibited growth, you know you have to use one of these two formulas, and it's up to you which one you want to use. Normally, you know, I guess to be safe, I would probably, if I saw the word continuous, use this one. Otherwise, use that one, but really both of those will work. All right, and then I want to just quickly do the next ones. The next ones are a little bit different because they always say each year. So when they tell you it's each year, now you're thinking about the annual compounding interest. And that's this formula that we had when we talked about annual interest as far as loans and things like that. So that we can talk about populations with this. So the final amount or population is equal to the initial amount or initial population times 1 plus your rate of increase, annual rate of increase, raised to the t, and the t is in years as well. Okay, the time is in years. So you're just using that basic annual interest rate. So when it says each year, that's what you're looking for. So each year the population decreases by 5%. So I took 1 minus 5%, which means I'm left with 95% is my base. If the year begins with 230, what is the population after 10 years? So my time is 10. So I just take 230 times 95.95 raised to the 10th. This is what I got, and I rounded that to 138 rabbits. Okay. Number 12, also a per year one. Assume the population increase is this percent per year. So once I saw that it was per year, I used my annual interest rate. It wants to predict when the population reached 20,000, so that's my amount. The initial amount was 42. 1 plus my percent, which is 0.0225, raised to the t. I want to know when, so I'm solving for t. So I divide by 42,000. I got about this. I wrote that down. I left it on my calculator, but it was about 4.762. I took the common log of both sides. So that's what you see over here. Took the common log of that amount that I had on my calculator. And again, I used the power property, but the t out in front where I took the log of this side. And then to solve, I just had to divide by the log of 1.0225. And I got about 70.14. So that's how many years, but it says predict when. If time 0 was 1910, 70 years from that would be 1980. So make sure you answer that question. Okay, so again, that's per year. I think I have one more over here that's per year. Again, it says each year. This is decreasing, so that means I'm going to take 1 minus 0.024 raised to the t power. The initial amount was 123,000. I want to know when, I want to know the time, when it is 90,000. So I divided by 123,000, took the common log of both sides, used the power property, put that t out in front, so I had the log of this fraction, the thousands canceled out, so I knew I didn't have to rewrite those. So the log of that equals t times the log of 0.976, so I divided by that log of 0.976, and I got about 12.86, so I just rounded that to 12.9 years, because remember t is in years when you're talking about annual interest. Okay, so anytime you see that each year, you know that you're using that annual interest or annual increase. This is the rate of increase. If it's a rate of decrease, you subtract that amount. Okay, so that gets you through number 13.